In this video, we present a proof-of-concept demonstration on the enablement of cross-framework communication within the 6G-Cloud system, including request-response interactions, information and data exchange, as well as model updates. Our demo highlights collaborative interactions among different 6G-Cloud frameworks, including the Management and Orchestration Framework (AIMLF), the Cloud Continuum Framework (CCF), and the Artificial Intelligence and Machine Learning Framework (AIMLF). The architecture, workflows, and results we present are the outcome of joint efforts by 4.Infinity and the University of Murcia. Here is the overview of the POC scenario. Starting from the bottom of the figure, the physical infrastructure layer includes the UE and IoT devices served by radio units, as well as the edge and cloud servers that host the virtual network functions, VNFs, of a network service. The resources marked in green constitute a resource partition for a particular network service. Moreover, a monitoring agent software component is deployed in each edge/cloud server, collating time series metrics that include the CPU and memory utilization, energy consumption, etc. Going step by step in the POC scenario, after initializing the threshold used for anomaly detection as step 0, the first step is to collect the time series of the buffer state report (BSR) metric associated with the NS through the Network Function Manager. The collected data are stored in the MOF-sourced monitoring database (MSMDB) in AIMLF. In step 2, the latest metrics are used to infer the pre-trained model for CPU utilization forecasting based on the status of the user buffer. The predicted values are then assessed by the anomaly detector, in step 3, to conditionally trigger CPU overload events. On anomaly detection alert, the NSDIR communicates the corrective action to the CCF resource orchestrator, which applies server scaling operations, step 4. In parallel, the performance monitoring module co-hosted in the MOF continuously evaluates the predictive performance of the running ML model. Specifically, in step 5, the performance monitoring module raises a performance degradation alarm, which drives the NSDIR to request a model retraining operation from the AIMLF, step 6. In the following step 7, upon an interaction cycle between MOF and AIMLF for initiating a fresh data stream collection, the recent dataset is utilized to retrain a new predictor, which is finally stored in the model database, as shown in step 8. Finally, the new model is served to the MOF for real-time inference, replacing the older version of the low-accuracy model. This process is performed iteratively to dynamically adapt the CCF resources and periodically update the ML model when needed. In this slide, you can see the architectural implementation of the demo scenario, consisting of 3 main components. Namely, the CCF components that provides the hardware resources to virtualize the network service and the NSDIR, the MOF component that manages the behavior of the overall system and the AIML framework that provides AI or ML pipelines for training models. The communication buses between these frameworks are implemented through Eclipse Zeno, allowing the query/reply for simple interactions, as well as the pub and sub operations for long-lasting interactions. The messaging configuration used for this demo is shown in the figure. The interactive elements in the demo scenario include the following. First of all, the publisher is an interactive element that defines a publisher on the concrete topic. In addition, the subscriber role defines an element that subscribes to the specific topic. Finally, the queryable operation defines a queryable object on the topic. To demonstrate the interactions and dynamic reconfigurability between MOF and AIMLF, we have initially deployed an ML model that is for online inference. Thus, assuming that the pre-trained model is up and running in the MOF and its performance is degraded, the demonstration starts with the NSDIR sending a model retraining request to the AIMLF. The AIMLF then requests the metrics list from the running network service, with the MOF responding with the list of these available metrics. Then, the AIMLF sends a request for CPU utilization data stream collection and subscribes to the key Zeno topic for receiving the new stream. This data stream provisioning is internally handled by the MOF, which spawns a monitoring thread that publishes the collected data periodically to the respective Zeno topic. The collected live data is used to build the training pipeline inside AIMLF, resulting in an updated version of the forecasting model. Once the model is stored, AIMLF notifies the NSDIR for new model availability and, upon deployment request, the most recent model is deployed in the service orchestrator of the MOF, to be used for online inference.
We will now show the interactions between the AIMLF and the NSDIR to create a fresh data pipeline. To begin the demonstration, we generate user traffic within the virtualized network. This is done by initiating a ping command from the user equipment to the internet. For this demo, we use packets of 1400 bytes, sent at intervals of 0.1 seconds. Once the traffic is initiated, we can observe uplink activity in the GNB logs, specifically in the uplink bitrate statistics. The GNB and the UE are both virtualized, using ZerMQ as the driver to enable their communication. Next, we open both the AIMLF and AIMLFE logs in order to monitor the process. While observing these logs, we will start the NSDIR application and open its log as well. The NSDIR triggers the retraining of a model by requesting it to the AIMLF. The retraining may be initiated, for example, because an anomaly has been detected, the model's performance has degraded for some reason, or the model has become outdated. Upon reception, the AIMLF will initiate the retraining process by first asking to the NSDIR for the available metrics to be used. This requires the AIMLF to communicate with the AIMLFE, which will internally retrieve this information from the MSMDB. Then, the AIMLF will select a subset of metrics for retraining the model and requests to the AIMLFE the creation of a dedicated data pipeline to receive them. Once the data pipeline is established, the data will start flowing and the AIMLF uses the incoming metrics to retrain the model. At this point, the AIMLF is ready to perform the retraining of the model based on the newly gathered data. In this context, we show the execution of the training pipeline. The components are showed in the Kubeflow UI. The pipeline comprises of the following steps. First, we have the data acquisition and pre-processing. Then, the training FO the model takes place, followed by an evaluation procedure. At last, there is a serving component, which creates an inference service for the deployment of the trained model. The trained model is also stored in the MLflow database, where we can depict some metrics or artifacts about its performance.
After the retraining is finalized, the NSDIR performs a request for model deployment. A Zeno session is then initialized and the AIMLF publishes the new model to a specific topic. NSDIR receives the model as a subscriber to this topic and saves it for inference. At last, the trained model is deployed and used for online inference using real-time data. Finally, to improve efficiency, the data pipeline that was previously created by AIMLF is terminated. Thank you for your attention.